All right, okay, guys, let's start, okay? Yeah, if you have any question, you can ask after the class, okay? So we have office hour from 4 to 5, okay? 4 to 5, okay? All right, so let's finish here some kind of marketing drawing question and also synthesis design question in the discussion worksheet first, okay? And then we continue chapter 19, okay? All right. So for the first one, it's kind of intramolecular kind of imine information. Okay. So for imine information, always have to do it kind of at the acid conditions. Okay. Because the amines kind of not strong enough to open the CO bond. Okay. So you have to make the activated. Okay. So the first step. Okay. Pick up these protons. Okay. And then you generate kind of we call the activated kind of the amine. Okay. Carbonyl compound. Okay. Right, and then falling kind of the lone pair electrons on the nitrogen K attack carbonyl carbon K. Open the CO bond K. So here you generate kind of ring, okay? So should be kind of 6-member ring, okay? But if you want to more accurate kind of you can count kind of carbon numbers, okay? So you can do here, okay? So 1, 2, 3, 4, 5, 6, okay? 6-member ring, right? So 1 should be nitrogen, okay? 2, 3, 4, 5, 6. Okay, nothing on kind of 2, 3, 4, 5. Okay, but here the on the 6 carbon. Okay, so you have OH group. Okay, and there's 1 extra hydrogen here. Okay, and then 2 hydrogen on the amine. Okay, right. And then falling by some kind of intramolecular kind of the proton transfer. Okay, so the lone pair electrons on the oxygen pick up this hydrogen and then give it back to nitrogen. Okay. That you can convert it to kind of the beta-alanine group kind of water. Right. Okay, so next kind of lone pair electrons on the nitrogen, okay, shift back, okay, so generate kind of the CN bond, okay, and meanwhile kick off the water, okay. Right, so that's the keep in mind not done yet, okay. So you have to do one more step, okay, remove the nitrogen, okay. So remove nitrogen hydrogen, okay. There's 1 extra hydrogen here, okay. Yeah, you need to remove this one, okay. So this one, pretty easy, okay. Pretty much is another water coming, okay, pick up this hydrogen and then give it back, okay. And let's give you the final product, okay. So that's why this reaction, okay, so the acid is catalyzed, okay. So very beginning, you lose 1 proton, okay. After oral reactions, okay, so you gain 1 proton in the systems, okay. Yeah. So make sure you know how to draw this mechanism, okay. Yeah. So remember chapter 18, there are totally 4 required mechanism. Okay, so that's imine formation is one of them. Another one kind of Grignard reaction and Wittig reaction and the addition of HCN. Okay, so Wittig reaction is showed here. Okay, so this one kind of pretty good one. Okay, so show the kind of from yearly the synthesis until kind of the general kind of CC bond. Okay, right. So we do it stepwise. Okay. Transform the force thinking attack kind of the first step is actually kind of we generate kind of yearly first. Okay, so SN2 reactions. Okay. All right, so that's first step. Okay, so they're kind of BR minus. Okay. Okay, and that's not yearly so far. Okay, so you have to kind of apply strong base. Okay, so that's the butyl lithium coming in here. Okay, so butyl lithium kind of very strong base. Okay. Yeah, deprotonated kind of the 1 hydrogen on the kind of the methyl bromide. Okay. So that you generate kind of real yearly the reagent. Okay. Platform phosphine is kind of. Yeah. All right, and then this yearly region you can draw the resonance structures. Okay, so that's just the PC bond. Okay. No matter, okay. Now we can draw the kind of a vertical reaction. Okay, so vertical reaction, yeah, when you draw it, okay, so yeah, make sure you align the kind of aldehyde ketone in the right directions. Okay, so here, okay, so yeah, phosphorus has kind of positive charge, and then carbon has kind of a negative charge. Okay, so you want kind of the oxygen close to the phosphorus. Okay, so yeah, this one oxygen, and then carbon to the kind of the close to this the negative charge species. Okay, the reason for that kind of you have to make sure that these two kind of charge matched. Okay, positive match kind of partial negative, and negative match with partial positive. Okay, right, and then the real nucleophile kind of this the C minus attack kind of the carbon carbon open the CO bond. Right. Okay, and then falling kind of this is kind of positive charge, this is negative charge kind of easily build up kind of the some kind of the square structure. Okay. Yeah. So that's we generate kind of this intermediate. Okay. And then there's some kind of the shift electrons. Okay. Quickly shift. Okay. So first one, the CP bond break up. Okay, and build up kind of a C bond, and then CO bond break up. Okay, and then build up kind of PO bond. Okay, and then eventually give you kind of a final product. Okay. CH2. And then trifluorophosphine oxide. Okay, so that's the vertical reaction. Okay, so make sure you know how to draw it. Okay, so very likely there's kind of similar question in the kind of exam tomorrow. Okay, right. So next kind of synthesis design questions. Okay, synthesis design question. Okay, so the first one actually not hard. Okay, the first one you can clearly see kind of there's kind of actual two carbon. Okay, kind of 1, 2, 3, 3 carbons. Okay, add to actually kind of one, two carbons. Add to kind of here carbonyl carbons. Okay, and so that means kind of we need to use some kind of the carbon bond formation reactions. Okay, and here you cannot use a vertical reaction. Okay, so because the vertical reaction kind of you one kind of from carbonyl. Okay, so this one is kind of these two bond. Okay, so here you see the bond already here. Okay, so that's the cannot from kind of a vertical yielded region. Okay, so you have to only add one branch. Okay, onto this carbonyl group. Okay, so that's we can use Grignard reaction. Grignard reaction. Okay. And Grignard reaction 有这那个 alcohol easy to convert 可能 alkene. Okay, we do the dehydration. Okay, so overall reactions kind of here. Okay, so we have kind of the Grignard reagent. Okay, so if you like, you can also do the workup. Okay, so two-step. Okay, so second step. Okay, which kind of some acid. Okay, but in the exam quiz. Okay, so if you didn't show kind of workup, probably okay. Yeah. You generate some kind of this add two actual carbon onto the carbonyl group. Okay, so open CO bond. Okay, and next step. Okay, so we just kind of do the dehydration. Okay, so that's we learned before. Okay, so elimination reactions. Okay, so we for the kind of xanthate fruit and kind of most the branched kind of alkene. Okay, so lose one hydrogen from here and lose one OH group here. Okay, that's the dehydration. Okay, kind of final product. Okay, pretty straightforward. Okay. Okay, and then we move to the next one. Okay, so next one kind of more challenging. Okay, so looks like some magic happened. Okay, so the CO bond we're beginning at the middle carbon, eventually at kind of the end of the carbon. Okay, so for this reaction. Okay, so you have to try to generate some handle. Okay, onto kind of terminal carbon. Okay, so that's kind of put functional group on it. Okay, so the handle we can generate kind of through elimination reaction, CO bond. Okay. To generate kind of elimination reaction product. Okay, so we have to kind of do elimination reactions. Okay, so this has to convert kind of the living group. Okay, so that's we can do dehydration, same thing. Okay, so that means kind of this CO bond we need the convert kind of alcohol. Okay, so that's the first step. We can do the sodium boron hydride yeah, reduction, okay. Or you can do kind of lithium aluminum hydride reduction, that's fine, okay, both okay. Yeah, OH, okay. Right, and then we do the dehydration, okay. So that's you can generate kind of double bond, okay. So for gas, okay, so normally you heat little bit, okay. So similar reaction like here, okay. And so yeah, if you want to convert kind of the OH2 Br or Cl and then do kind of base-based kind of the E2 elimination, that's also fine, okay. Yeah, but here it's gonna just do it directly with okay, dehydration, okay, remove one water, okay, and that will generate kind of handle on the terminal carbon, okay. Right, so now we need to put some kind of handle on here, okay. So that's the addition reaction. Addition reaction that's you for kind of anti-Markov Nichols group, okay. So that's we only learned one reaction kind of the hydrogenation oxidation reactions, okay. So that can put the OH group onto the terminal carbon, okay. All right. Okay, so that you put some handle on, okay. And then only one step left. Okay, how do we convert this kind of the terminal alcohol, primary alcohol into kind of aldehyde? Okay, so we learned one special reagent can do this. Okay, so yeah, that's the PCC. Okay, PCC can oxidize kind of the primary alcohol into aldehyde. Okay, just the one step. Okay, one kind of give kind of over oxidation. Yeah, okay, give kind of Carboxylic. Okay. All right, so that's about kind of the discussion. Okay. And a couple things about kind of the exam tomorrow. Okay, so yeah, exam tomorrow I will open at 6 p.m. and then close at 12 p.m. Okay, so if you have a conflict schedule, okay, so for example, I have kind of have to work or kind of have kind of a lot of class during the daytime. Okay, so yeah, please email me. Okay, so yeah, and then I can open the exam for you at another time. Okay, and so it has been reported by some students. Okay, so just during the exam quiz. Okay, so the system just kicked them off. Okay, and then cannot log back. Okay, so in this case, after your exam, okay, make sure check you how much time did you spend. Okay, so yeah, for example, you didn't finish exam paper, but when you check the time, you find I only used 40 minutes. Okay. So in this case, please email me, okay? I can give you time back, okay? So give you extra 20 minutes, you can finish the exam, okay? Yeah, just you check your time, okay? So no rush, okay? So I will keep my Zoom open, from 6 until the 12 p.m. tomorrow, okay? So yeah, so if you have some technical problem, okay? So yeah, for example, you kind of computer freezing or kind of just some logging, okay? So yeah, login kind of Zoom, let me know, okay? Or you can email me, okay, but I cannot check my email often, okay. So yeah, the better way to do kind of login kind of Zoom, okay. All right, so that's about kind of exam, okay. Again, okay. So yeah, I have office hour, okay. So from 4 to 5, okay, today, okay. So just after this class, okay. So if you have any question, okay, so any thing kind of let me want to go through kind of the homework, you just kind of keep your Zoom open, okay. All right. So any question about the exam or kind of chapter 18? No. Okay. All right. Okay, so in this case, if you have question, okay, just please type in the chart window, okay. Okay, so in this okay, so far pretty much similar like exam 1, okay. So we are like 25 questions, okay, and for the chapter 18, okay, so we already summarize all the reactions, okay. So we have the end of the chapter 18, okay. So yeah, please look at the video or kind of look at your notes, okay. So that's chapter 18, we didn't cover too many reactions, okay. And one good thing is kind of because we haven't test chapter 18, okay. So in this case, I will say 40% question will form 40 to 50% question will form kind of a chapter 18, okay, and then yeah, the 25 from kind of a chapter 11, 25 from kind of chapter 17, okay. So yeah, that means kind of make sure you know the kind of chapter 18 where, okay. All right, any other questions? All right, okay, so if there's no further question, okay, we continue study kind of the chapter 19, okay. So chapter 19, we start talk kind of the convert between kind of the acid, also acid derivatives, okay. And last time we talked about kind of how to make ester from kind of acid, okay. So yeah, these two have very similar reaction, okay, reaction rate, okay, similar reactivities, okay. So pretty much should be equilibrium reactions, okay. And the general reactions showed here, okay. And for these reactions, okay, so to push reaction to the ester directions, okay. So either you remove kind of product, okay. So normally remove water or ester. Ester may be either, okay. So you kind of just distill out, okay. Or kind of add actual starting material, okay. So normally just kind of add alcohol, okay. So alcohol kind of cheaper, okay. So that's can push equilibrium to the kind of the right, okay. Right, and then for this reaction, kind of one of the required mechanism, okay. So the Fischer esterification actually kind of pretty important, quite mechanism, okay. So in this case, I draw here, okay. So you guys can also kind of try to follow me, okay. Draw these three reactions, okay. Right. Okay, so because the alcohol as a nucleophile, alcohol kind of quite a weak nucleophile. In this case, that's why we have to kind of use the acid as catalyst, okay. So try to make more active kind of the carbonyl compound, okay. So the OH group pick up proton first, okay. Yeah, so you generate kind of we call the activated kind of carbonyl group, okay, activated, okay. So and then the alcohol coming, okay. Open the CO double bond, and you generate something like this. All right, okay, so there's kind of intramolecular kind of the proton transfer, okay. And so these lone pair electrons on the kind of OH, okay. So maybe here OH, okay, will pick up the proton from this original kind of alcohol, okay. So if you do kind of intermolecular transfer, that's probably also okay, okay. So that's just some kind of the water or some base pick up this the hydrogen and then give back to kind of this OH group, okay. That's both fine. But intramolecular reaction kind of much likely kind of right here the mechanism, okay, because let's see just see the low kind of entropy cost, okay. All right, so you generate kind of the good living water group, okay. Right, and then lone pair electrons on another OH group shift back, kick off this water. All right. Okay, so no done yet. Okay, so some base coming, we will pick up kind of the hydrogen on the carbonyl group, okay. So normally just kind of another water or maybe some kind of other base, okay. Give you final ester. Now, if you want to add lone pair electrons, can add, okay. Right. So that's the whole process, okay. And for the reality, the whole process actually kind of the reversible, okay. So all the steps kind of reversible, okay. Yeah. All right, and for this reaction, okay, so give you guys probably a couple of example, okay. Yeah. So that's actually kind of the most common way to make kind of ester, okay, because the acid kind of shape. Okay. Normally we don't kind of use the acid anhydride or acid chloride to make kind of ester. Okay, so we from kind of the acid just directly, okay, and do the Fischerification. Okay. The first one, benzoic acid react with kind of methanol, okay, and then we use some kind of sulfuric acid, okay, sulfuric acid kind of best catalyst for this reaction, okay. Kind of ester, okay. And so another product, if you want to draw it kind of water, but if you don't want to draw it, that's fine, okay, no big deal, okay. Right. And then second one kind of actually kind of more interesting kind of intramolecular kind of the ester formation, okay. Right. Remember I said kind of whenever you see some kind of long carbon chain linked to the two functional group, okay, that means kind of normally we will call kind of intramolecular reactions, okay. So you can alcohol, carboxylic, okay, so that's typical kind of the acid, okay, typical kind of Fischerification reaction conditions, okay. So pretty much this OH coming kick off this oxygen, okay. So if you like, you can draw kind of maybe you do it kind of a little bit ugly one, okay, and then we draw the pretty one. Yeah, so that's it, okay. Pretty one kind of you count here the atom numbers, okay, 1, 2, 3, 4, 5, 6 membrane, okay. Yeah. So this one actually will generate here some kind of we call it internal cyclic ester, okay. Cyclic ester has kind of a very special name called kind of lactone, okay. Yeah, quite often you see heard some kind of lactone, okay. Lactone actually kind of just refers to kind of cyclic ester, okay. Yeah, cyclic ester. Okay. All right. And so that's how do we prepare ester, okay. Next, okay, so questions, okay. For the second couple. So the mechanism for this one, okay, so that's similar here, okay, so pretty much, okay, so the oxygen, carbonyl oxygen pick up the hydrogen, okay, make kind of more active kind of carbonyl group, okay, right, and then falling kind of the OH kind of attack kind of carbonyl carbon, okay, open the CO bond, okay, and then falling kind of this OH become kind of water, okay, so through kind of intramolecular kind of the proton transfer, okay, and then falling kind of kick out the water, okay, eventually you generate somehow kind of the activity kind of ester, okay, so remember remove kind of these hydrogens, okay, give kind of final ester, okay. So that's kind of important mechanism, okay, so make sure you know how to draw it, okay. Yeah, so I will promise you, okay, so this mechanism I will test in kind of future exam or quiz, okay. Yeah. Right, okay. So next kind of that's it, how do we make ester, okay. So the following, okay, so we will learn how to make the carboxylic, okay. So that's a 4, okay. Yeah. So carboxylic kind of the easiest way is kind of just from kind of acid chloride and also the anhydride case, so because acid chloride and also anhydride too reactive case, so if you react with directly with the water case, so if you want to make it the carboxylic case, so keep in mind, okay, just use water as a nucleophile, okay. So if you want to make ester, okay, so remember use alcohol, okay, acid use water, okay. And for this one case, so if you start with kind of the acid chloride or kind of acid anhydride, okay, so that's kind of just pretty much a simultaneous kind of reaction happened, okay, because these two kind of too reactive, okay, so they're quickly hydrolyzing kind of carboxylic, okay, so that's why kind of if you have these two reagents, okay, so normally kind of make sure they're kind of water free, okay, so there's no water in your reactions systems. Okay, so remember in the previous lab. Okay, so the fluid chloride acylation reactions. Okay, and then I told you guys kind of make sure there's no water. There's no water. Okay, reason for that kind of water will react with kind of acetyl chloride. Okay, and give kind of carboxylic. Okay, if you have carboxylic. Okay, so no way you can have kind of reaction happen. Okay, so to prevent kind of the hydrolyzed case, so make sure we have kind of water free. Okay. So but that's actually kind of not so common. Okay, so for the acid anhydride, keep in mind. Okay, so after reactions. Okay, so generally kind of two acid. Okay, so pretty much kind of the 2OH. Okay, 2OH. Okay, but that's actually kind of not so common. Okay, so can this here. Okay. So acyl kind of the chloride or anhydride kind of the hydrolysis. Okay. This is kind of the more expensive one. Okay, because the acid quite cheap. Okay, so we try to make some cheap chemical from kind of expensive one. Okay, acid anhydride, acid quite expensive. Okay, so that's the last common one. Okay, the most common kind of the ester hydrolysis. Okay, so because the ester kind of the pretty cheap. Okay. So for ester hydrolysis, okay, so there are kind of two conditions can do it. Okay. So one is kind of under basic conditions. Okay, you use kind of aqueous base. Okay, like sodium hydroxide or potassium hydroxide. Okay, and heat it up. Okay, and then you do kind of work up. Okay, so normally kind of add a little bit acid. Okay, so eventually give kind of acid. Okay, so this reaction kind of has special name. Okay, so called kind of saponification. Okay. Saponification. Okay, so that's the basic conditions. Okay. And the general reaction for these reactions kind of show you guys here. Okay. All right, have some ester. Okay, and then react with the water, and then under the very strong base condition. Okay, so normally kind of the OH minus. Okay. So for this reaction, okay, so two steps you have to do kind of acid work up later. Okay. Once reaction is done. Okay, so you generally kind of one kind of carboxylic. Okay. And then plus the alcohol. Okay. So that's the quite often. Okay, so different from the other ester or acid conversion. Okay, so don't need to draw the another product. Okay, so another inorganic. But for the ester hydrolysis. Okay, normally you have to draw both. Okay, because another product is also organic compound. Okay. Shown here. Okay, show both the carboxylic product and also alcohol product. Okay. And so for this reaction, okay, because the first step is very strong basic conditions, okay, you generate carboxylate ion. Okay, so right. So that's why you have to do kind of the acid work up. Okay, and then convert the to kind of final acid. Okay. All right. So here's a similar question come up again. Okay. So why we have kind of ester and those carboxylic. Okay, they have similar reactivities. Okay, and then this reaction kind of push forward. Okay, complete. Okay, so you see kind of as use kind of single arrows. Okay, a reason for that kind of I have to draw you guys kind of mechanism. Let's see. So that's a mechanism kind of the acid actually kind of not real product. Okay. The carboxylate ion is real product. Okay, draw it one by one step. Okay. Right, so this one, the reaction mechanism is also required. Okay, so please write it down. Okay, record it. Okay, right. The first step kind of the OH minus coming in. Okay, right. Open the CO bond. Okay, because OH minus kind of relatively stronger kind of the nucleophile also kind of base. Okay, so no problem. You can open the CO bond. Okay, once it's open. Okay, you generate kind of this tetrahedral intermediate. Okay. Okay, And then the lone pair electrons on this oxygen come back, okay, kick off here the OR, okay, so OR prime, okay. So yeah, that's some people said kind of OR price kind of yeah very strong base, okay. So yeah, less likely, but yeah, the reality that's reaction yeah indeed happen like this way, okay. The reason for that I'll explain it soon, okay. Right. So it looks like you kind of catastrophic, but yeah, because this whole reaction under the acid basic conditions, okay. So in this case, yeah, the OH come back, okay. So another OH minus can pick up the hydrogen, okay, and then give you kind of a carboxylate, okay, ion. Yeah. So that's yeah, a real product for the first step, okay. Yeah, real product for the first step, okay. And then you do the acid kind of yeah work up, okay. So the second step, okay. And then you turn kind of yeah carboxylic, okay. Yeah, so that's here the yeah whole reaction, okay. So why this reaction kind of yeah yeah irreversible and also can yeah push to the end, okay. So the reason for that kind of yeah this is kind of real yeah the product, okay. So this is the real product, okay. And then the for carboxylate, okay. So yeah yeah oxygen has already yeah the minus charge, okay. So yeah you cannot kick off kind of generate kind of oxygen yeah 2 minus, okay. So that's yeah the extremely unstable, okay. So that's much more stable than OR, okay. So this one is much more stable than OR. So that's why kind of yeah you can push equilibrium to the right, okay. And that's yeah also yeah yeah here, okay. So you can see kind of yeah this yeah the reactivity letters, okay. So yeah the yeah carboxylic ion, okay. So it's the most stable species compared with esters, okay. So because yeah this selenium kind of yeah very unstable compared with kind of OR minus, okay. So that's yeah you can yeah prepare kind of yeah yeah unstable yeah the product, okay, from yeah relatively yeah, more stable starting material, okay. Kind of yeah prepare the most stable product from kind of yeah the relative unstable yeah starting material, okay. And then whole reaction kind of yeah also irreversible, okay. And here's kind of yeah explained kind of from energy diagram, okay. So yeah, for the yeah first yeah the step reactions, okay. So yeah, suppose you generate kind of a capacity base has kind of same reactivity as kind of ester, okay. And but yeah this yeah acid quickly reacts with kind of yeah some base, okay, and then generate kind of carboxylate ion, okay. Carboxylate ion kind of yeah much more stable, okay. So that's kind of yeah whole equilibrium kind of shift to the right, okay. And also, yeah, one thing you have to keep in mind, okay, for these reactions, okay, so we have the real ester, okay, so we have the base, okay, so real base kind of yeah, consumed during the whole reactions, okay. So that's yeah means each mole of the ester you need the require each mole of ester you require 1 mole of the yeah base to push reactions, okay. So the base is not a catalyst, okay. So the base actually kind of become one of the part of the yeah you yeah final product, okay. So that's why you cannot kind of yeah just yeah use catalytic amount of your base, okay. All right. So that's the first way, okay. So do the kind of the saponification, okay. So under the basic condition, okay. All right. And then the second way is kind of yeah under the acid conditions, okay. So the acid condition actually kind of yeah actually kind of yeah exactly reverse of the process of the Fischer esterification, okay. So we call kind of yeah reverse yeah Fischer esterification, okay. Yeah, exactly kind of reverse whole process, okay. So that means actually kind of yeah as long as you remember how to draw the Fischer esterification yeah mechanism, okay. So pretty easy to draw the kind of yeah Ester hydrolysis under acid conditions, okay. And so, but here I still yeah want to draw you guys, okay, because that's kind of yeah the two important these reactions, okay. So the yeah whole reactions, okay. So okay, so first draw you guys kind of yeah general reaction first, okay. So general reaction, okay. So ester, yeah, with some kind of yeah, the water, okay, and then some acid, okay. So this time kind of only one step, okay? So you don't need to do some any workup, okay? Yeah, once reaction is done, you just carboxylic acid and then plus the alcohol, okay? And then this reaction different kind of basic condition, okay? So that's reversible, okay? So yeah, that's you have to draw kind of the double head arrow, okay? All right, so now again I will draw kind of reaction mechanism for you guys, okay? So pretty much the first step kind of the similar thing, okay? So otherwise kind of under acid condition, the first step always kind of the oxygen pick up the proton, okay? So that's the pretty easy, okay? So you guys just remember, okay? So acid condition always kind of first step kind of pick proton, okay? Because under acid condition normally kind of nucleophiles quite weak, okay? Cannot directly attack carbonyl carbon, okay? Right, and then we just kind of we call the activated kind of carbonyl, okay? Right, and then now the water coming, okay? Open the CO bond, okay, and then you just kind of tetrahedral intermediate, okay? Right, and there's kind of the intramolecular kind of the proton transfer, okay? So this OR pick up proton from the water, okay? And then become kind of more kind of the good link group, okay? So the alcohol, okay? Right, so now ready to kick off this the alcohol, okay? So either OH can do it, okay? So doesn't matter, okay? So for example, the top one, lone pair some electrons on the aqueous can come back, kick off the OR, okay? And then you generate some kind of the final intermediate, okay? Right. And then some kind of base come in, okay? So normally speaking, kind of this reaction done at water, okay? So water will be the base, okay? Pick out this hydrogen and eventually give you kind of a final carboxylic acid, okay? Yeah. So that's the whole reaction process, okay? So for this reaction, okay, so the mechanism exactly same kind of reverse way of the Fischer-ification, okay? So as long as you remember one, it's easy to kind of remember another one, okay? So pretty much exactly same thing, okay? So just kind of you do it kind of backward, okay? So just kind of the ester, okay? You do it kind of forward, just kind of acid, okay? So you just remember one, it's easy to remember another one, okay? Right. And so like I said, kind of this reaction kind of reversible, okay? And but if you want to kind of go to kind of acid directions, okay, just add a large amount of water, okay, and distill some kind of alcohol, okay, should push equilibrium to the right, okay. All right, so here's kind of a little bit summary, kind of summarize the saponification and also the acid-based kind of reversible kind of the Fischer-ification, okay, so called kind of acid hydrolysis kind of acid catalyzed hydrolysis of the ester, okay. So for the acid conditions, okay, so the acid kind of you only need the catalytic amount, okay, because the very beginning you lose one protons, okay, but eventually, okay, so you give this proton back, okay, to the system, okay. So you can recycle the protons, okay. But for the base, okay, like I said, kind of the base action of real region, okay, so you need kind of equal molars, okay. The second difference kind of acid condition kind of reversible, kind of basic condition kind of irreversible, okay. So in this case, normally speaking, kind of if it's not other special reasons, okay, so we do the kind of reaction kind of under the basic conditions, okay, because kind of the push equilibrium kind of just to the end, okay, so don't need kind of stop at any stage, okay. So that's something keep in mind, okay. All right. Okay, so next I will give you guys kind of a couple of examples, okay. make sure that yeah, you know the draw kind of mechanism. Okay, so for the Fischerification and also the yeah, basic condition hydrolysis of your ester or kind of ester conditions. Okay, so those here the all are required. Okay, so yeah, pretty kind of fundamental mechanism. Okay. Right. So for the first one, okay, I drew kind of here the acid conditions. Okay. Right. So we have this acid, okay, ester, okay, this ester, okay. So yeah, yeah, use acid. So that's the aqueous acid, okay. So yeah, H3O plus, okay. So that's the typical kind of the yeah, acid aqueous solutions, okay. So once the reaction is done, okay, so keep in mind, okay, you need to draw both products, okay. So pretty much the yeah, you break up bond here, okay, break up bond, okay. So the carbonyl part, okay, pick up the OH, okay, and then yeah, the alcohol part pick up kind of the yeah, a hydrogen, okay. Yeah, that's for that, okay. And another one, okay, so yeah, that's actually kind of yeah, more interesting, okay. Right. So we have this lactone, okay, cyclic ester, okay, and then let's do kind of yeah, the hydrolysis of this one, okay. So this time I'm going to kind of yeah, use the yeah, saponification reaction condition. Okay, saponification conditions, okay, so we need kind of yeah, the two-step reactions, okay, two-step, okay. So yeah, you do some acid workup, okay. Right, so that's the first time we see kind of yeah, we do the reversible kind of yeah, ring-forming reactions, okay. So don't worry, okay. So that's the still same thing, okay. So yeah, you need to know where's kind of bond break up, okay. Where's kind of yeah, that's actually here, okay. That's break up, okay. Break up, okay, and then the OH goes kind of carbonyl carbon, okay, and then hydrogen goes kind of the yeah, this yeah, the yeah, single carbon, kind of single bond kind of the oxygen, okay, right. And then pretty much you'll generate kind of yeah, something like this. Yeah, count carbon number 1, 2, 3, okay, 1, 2, 3, okay. Yeah, that's the final product, okay. All right. Okay, so that's yeah, how do we make it the yeah, acid, okay. And the next kind of yeah, we'll learn how to kind of yeah, make kind of yeah, actually kind of also acid, but yeah, from kind of yeah, we call kind of the hydrolysis of the yeah, amide, okay. Right. So for amide hydrolysis, we actually kind of yeah, not so easy, okay. So reason for that kind of yeah, we know kind of the amide kind of more stable than kind of carboxylic, okay. So you try to make kind of last stable one from more stable one, okay. That's yeah, pretty tough, okay. So actually this reaction normally do it at kind of the either under acid condition or basic conditions, okay. So both are pretty tough, okay. So yeah. For the acid condition, okay, so yeah, use strong acid and then heat and kind of aqueous solution for several days, okay, probably can get the reaction work, okay. Basic condition, similar thing, okay, so yeah, you use strong base and heat kind of in aqueous solutions for several days, okay. So why is this reaction can work, okay? So reason for that actually kind of yeah, the amide actually kind of the NH2 minus not real yeah, leaving group, okay. The real leaving group is kind of the amine, okay. Yeah. So for this one, okay, so we are the actually the yeah, NH2 pick up the yeah, hydrogen, convert kind of the ammonium, okay. So that's the actually kind of the better leaving group, okay. And then you kind of water coming, okay, replace kind of the yeah, ammonium. Right. And so for the ammonium, okay, once it's get kind of into the solution, okay, so quickly pick up another protons, okay, become kind of ammonium, okay, ammonium become ammonium. Right. So that's the yeah, make it kind of totally no nuclear facility. Okay, so cannot what kind of nuclear anymore. Okay, cannot push back. Okay, so that's the reason. Okay, so we convert kind of better living group. Okay, and for the basic conditions. Okay. Similar like the saponification. Okay, so driving forces kind of you generate the carboxylic ion. Okay. Yeah, so this guy. Okay, so that's the more stable than kind of the amide. Okay, so that's why I can push reaction to the right. Okay. And here they showed you some example. Okay, so for the basic condition. Okay, so once you done reaction, keep in mind you have to also do some kind of workup. Okay, that's shown on the top. Okay, so generally kind of the carboxylic. Okay, and then you acid workup. Okay, generally kind of final acid. Okay, and following kind of the do it kind of on the acid conditions. Okay, so this time people actually want this amine part. Okay, so that's why do a little bit the basic condition workup. Okay, so give kind of final amine back. Okay. Right. Although in our textbook set kind of you can get carboxylic from kind of amide. Okay, so from my personal experience. Okay, so the better don't do it. Okay, so when I was the PhD student. Okay, so I try to hydrolyze some kind of the amide into the acid. Okay, so high temperature cook like 3 days. Okay, so only get like 30 to 20% yield. Okay, very poor yield. Okay, so that's not ideal reactions. Okay, so in future, if you want to make acid. Okay, so just do the Ester Hydrolysis. That's the much better and also efficient way. Okay. Yeah, Gabriel reaction. Gabriel reaction kind of remember. Okay, so that's actually kind of So we generally kind of some protect kind of amine. Okay, so that's we use some kind of potassium hydrolyzed. Okay, that's actually kind of somehow like acid kind of hydrolyzed kind of acid condition hydrolyzed kind of amide. Okay, so eventually. Okay, so and then you release kind of amine. Okay. So that's actually kind of some kind of example for the kind of the acid hydrolysis kind of amide kind of under the basic conditions. Okay. Right. Okay, and then for the acid. Okay, so we can actually also prepare it from nitride hydrolysis. Okay, so nitride hydrolysis kind of let's see actually this is the 3. Okay. That's 4. Okay. So for nitride hydrolysis. Okay, so that's actually kind of pretty interesting. Okay, so the first step you can stop at kind of amide stage. Okay, so so overall kind of you have nitride. Okay, so and then normally you do it at kind of the acid conditions. Okay, so right. So for this reaction, actually, if you like, you can stop at kind of amide stage. Okay, amide. Okay. Right, but if you want to give little bit the push. Okay, so like high temperature or kind of the longer reaction time. Okay, so you can push it to kind of carboxylic. Okay, so really depends the what's reaction conditions. Okay, the reason for that kind of amide kind of the much more stable. Okay, so you can last stable one to the more stable one. It's easy. Okay, but the next step kind of need much more harsh conditions. Okay. And here shows you kind of one example. Okay, so if you reflux whole reactions. Okay, you can directly go with kind of the carboxylic. Okay, but if you want to kind of do a little bit mild conditions. Okay, so like the 40 degrees. Okay, so that can stop at kind of the amide stage. Okay, and so for nitride hydrolysis to kind of carboxylic. Okay, so that's also last common. Okay. And also poor yield. Okay, but in our textbook set kind of it's working, but that's working. Okay. Why we still study here? Okay, because this one can easily convert some kind of other halide into kind of carboxylic, okay, with one more kind of carbons, okay. So yeah. Yeah, you just do the SN2 reactions, okay, and then give kind of the nitric compound and then do the carboxylic, okay. But yeah, this way is kind of a relative less efficient, okay. So yeah, we learned another way to do it kind of in chapter 18, okay. So yeah, don't know anyone remember it, okay. So yeah, Grignard reactions, okay. Yeah, actually kind of we just did this lab kind of last week. Carbon dioxide, okay, and then you follow kind of acid workup, okay, can also give kind of same product, okay, yeah. Yeah, so that's just keep in mind, okay, so for the same starting material and also same product, okay, so you can use different route, okay, finish the conversion, okay, so that's the cool thing about kind of organic synthesis, okay. All right, okay, I guess let's see, okay, prepare amide we'll do it on Wednesday, okay, all right. And do you guys have any question about the chapter 19? Stop kind of recording.